So, welcome back. What we are going to do in the next series of lectures is to cover some of the important aspects related to the performance grading. So, before we proceed further, what we need to do is to have a kind of recap about what exactly is the performance grade. So, the moment we talk about performance grade, we are talking in terms of performance at high temperature, rutting, fatigue, intermediate temperature and low temperature. So, in all this it is the temperature which is the main criteria compared to whatever we have seen earlier for viscosity grading, wherein we measured few select properties at fixed temperatures. Here we are going to measure these properties over a range of temperatures and these specification parameters are going to be fixed. So, this is a complete transformation from the way in which we have been originally writing specifications for bitumen. So, there are some important issues that we need to recap before we proceed further. The first and foremost thing is the understanding that was developed related to the aging of binders. So, we realize that the performance of the material will depend on the aging to which it is being subjected to during the field conditions. So, we developed test procedures for short term as well as long term. Such detailed procedures were not available before in any of the grading system. The second thing that we need to understand is what is the relation between air temperature to pavement temperature. A detailed investigation was carried out, different long term pavement performance stations collected data and regressions equations have already been developed for relating the air temperature to the pavement temperature. Detailed statistical analysis also were carried out, so that one could have a expected temperature for the pavement for the design life. In India, in a limited amount of work, IIT Madras, we did some calibrations as well as some temperature contours were developed for the entire country for the minimum as well as the maximum temperature. So, this is the next aspect, which is the pavement temperature versus air temperature. The third and the most important thing is correlation of field to lab on one side and mixture to binder on the other side. So, the moment we start talking about rutting, we are talking about some phenomena, distress that happens in the field. Now, how do we really carry out a test in the laboratory to find out what is the expected rutting? That is the number one. Number two is, it is much easier to carry out experiments, investigations, model developments for binder rather than for mixtures, and since this performance grading is essentially tuned towards the binder, we also need to develop correlations between the mixture to the binder. So, the first is the relation between field to lab and then mixture to the binder. So, based on all these aspects, we came out with specifications so that one could measure all this in the laboratory. And another important aspect is the use of dynamic shear rheometer for characterizing the response of the material, and an explicit understanding that one should have enough background in linear. Of course, I have to emphasize that viscoelasticity to make these correlations and statement. There were also some limited amount of investigations carried out relating to the chemistry of the material. Nevertheless, they have not reached the level of fineness that we are really looking for. Then there were also some understanding about how modifiers are going to respond, and this was covered in separate lectures by Dr. Nivita on multiple stress creep and recovery as well as Dr. Padma. And these days there are also interesting connections are being made between mixed design and laboratory performance test, and this was covered in detail by Dr. Neetu Roy. Okay. So, what we will do is we will proceed further. We will look into 3 to 4 main aspects here. One is how do we really get these derivations for G star sin delta as well as G star y sin delta, number 1. Number 2, what are the specifications that one should write for low temperature PG in terms of bending beam rheometer as well as direct tension test, and then we will also make some statements about the intervalless performance grading, or for instance how do we really get a continuous PG grading. So, with that we will be able to conclude what we wanted to talk about as far as PG is concerned. Okay. So, now we will talk about how did we really get this PG criteria. The very first important thing that we need to understand is the fact that energy dissipation is the main criteria, and in fact in any constitutive assumption that one makes for a material, the first and foremost thing that we do is how the material will respond to any kind of loading conditions will basically depend on how the material stores energy as well as dissipative energy. And in fact, in some of the foundations of mechanics in which when people start writing explicit assumptions, the assumptions will not be made for the stress strain relationship, rather the assumptions will be made based on how the energy is stored and how the energy is dissipated, and using second law or reduced energy dissipation equation, appropriate constitutive expressions will be derived based on such assumptions. Okay. So, we do not need to get into all those details as part of the course, but the fact that the material dissipating energy, the amount of energy that is being dissipated in a sense tells us about how the material is going to perform, right. So, what really happens as far as the rutting is concerned, you are going to have repeated load on the field, and because of this there is going to be a permanent deformation or irrecoverable deformation, residual deformation, which you are not able to get it back. So, that means there is a substantial amount of energy that is dissipated during the process. So, that is as far as the energy dissipation part is concerned for high temperature. So, let us now start looking at it. Now, we can actually start talking about the energy dissipation in a nutshell, the overall thing, which can actually become very complicated for a viscoelastic material, really how to compute the energy dissipation for different kinds of loading. Rather, we are going to take a very simple aspect issue here is we are going to assume that the energy dissipation that we are talking about is in terms only of the viscous component, and we are going to say that the energy dissipated per cycle is an integral of the shear stress and the incremental shear strain. So, that is what we are going to do, and one could show that if you are going to have a sine wave, and we are not really talking about whether it is a stress sine wave that is being imposed or the strain sine wave that is being imposed, one can write the energy dissipation for that particular cycle as tau max, gamma max, sin delta. Okay. Now, this is the maximum shear stress, this is the maximum shear strain, and this is the phase lag. Okay. Now, let us little bit rewrite this by using the above form. So, what we are going to do is we are going to write this as G star as tau max. So, when we use this aspect here and rewrite, what we are going to get is pi times tau square max sin delta divided by G star. G star is the mod value of the complex modulus, and this is where we now need to make a clear distinction here. When we want to carry out an experiment to quantify the rutting that is expected in a material in the laboratory, we would like to do a stress controlled experiment, because we would want the strain to keep increasing. We do not want to control the strain, because we basically believe that the rutting that happens in the field is more due to the deformation, that is the irrecoverable deformation that happens. So, if I do a stress controlled experiment, so that means in which case the stress is constant, I could write that this energy dissipation is nothing but it is proportional to sin delta divided by G star. Okay. Now, we need to emphasize, and I am going to say it again, this is valid only for a stress controlled mode of loading applied in the form of a sine wave in the linear viscoelastic regime. Okay. Now, how do we really reduce it to rutting? So, what we need to do is, so I can write this in terms of sin delta by G star, or I can also go back and rewrite the same thing in terms of this, and if the response is purely elastic, what will really happen? If the response is purely elastic, what will happen to the phase angle? The phase angle is going to be 0, and if the, so in which case the energy dissipation is going to be 0. But if the response is purely viscous, what can really happen? The phase angle is going to be 90 degrees, in which case the energy, everything that is work that is done on the material is completely dissipated. Now, in essence, this particular relation tells you something about the energy that is being dissipated. So, if you really want to minimize this energy dissipation, what one could do is to ensure that this value is high or this value is kept low. Okay. So, this is the interesting crux here. Now, we need to go back and read the original document that was released by Federal Highways Administration. The report is given here. This says validation of asphalt binder and mixture test that measure rutting susceptibility. This is a report that was published 8 years after the first report for performance grade was released in 1992. This is a 2000 document. So, they very clearly write few things here, and most of the students here who are listening to this should understand and read this. You can even download this report. You should be reading from chapter 2, and in fact, if you read chapter 2 of this report, it is will give you enough information. Now, let me read it out carefully. In SuperPave only, the absolute value symbols were dropped for simplification purposes. Technically, the term should be described as G star. Now, if you have followed all our lectures, we have very clearly mentioned the dynamic modulus in the following. We never dropped the absolute value symbols there. Okay. But if you read the specification is just written only in this following way, and in fact, only in pavement engineering in SuperPave it is written specifically like this. Second, because most asphalt paving technologies have some understanding of the term modulus, the parameter sin delta by G star that was shown here earlier was inverted to G star by sin delta. Okay, so, that is how this G star by sin delta came. So, now what will really happen? As this parameter increases, the rutting susceptibility should decrease. So, this is the value that you are really looking at. Now, let us go back and look at what the specification says and read this carefully. As the parameter increases, the rutting susceptibility should decrease here. So, what is really given here, and this is something that we have seen in the earlier slide. It is written as G star by sin delta is given a minimum value. So, that means this much minimum should be there at any given temperature, so that there will not be any tendency for rutting. That is the basic idea. So, that means you are expecting this value to be as high as possible at any temperature. So, we need to understand this. So, if you recap and go here, originally we wrote it as sin delta divided by G star. So, if you really want to reduce the rutting, you want the energy dissipation to be the minimal possible, and if you really want it to be minimal, then you want G star to be higher or sin delta to be lower. Now, when we invert it, what we are really looking for is, you are looking for a specific value at least this much. If it is more than that, you are always, it is most welcome, but at least this much should be there. So, do not get confused between the minimum that is mentioned here and the minimum that we discussed in the earlier slide. So, this is the specification requirement for PG for rutting. Now, let us try and see how we do it for the fatigue. So, in the fatigue, again we need to understand, we will be focusing on a strain controlled experiment. Why is a strain controlled experiment mentioned here? If you really understand the fatigue process, fatigue damage process, we always normally we do an experiment in which the strain is controlled and some kind of a modulus value. I am going to, for the sake of convenience, I am going to call this as just as E. It could be any modulus, tangent modulus, secant modulus, dynamic modulus, whatever it is, and this is for the number of cycles. We expect that it will reduce something like this. So, that means you are applying a strain level sufficiently small for a large number of cycles, and we are interested to find out how much is the deterioration of the modulus value as the number of cycles increase. So, that means we should be able to control the strain here, because if you really want to simulate the fatigue process in the laboratory, you apply a load level such that the strain in the material will be sufficiently small, and then we keep accumulating the damage in an incremental way. So, now when I do in the strain control experiment, you can actually see this is the energy dissipation, which is what we wrote earlier, and all we are now going to do it, since we are controlling the strain, you are just going to substitute the value of tau max with the formula that we have used, and here for the sake of convenience, since we defined it this way in the earlier slide, I am going to write it like this: G star is tau max by gamma max. So, you substitute for tau max here, so that is going to be G star times gamma max into gamma max sin delta, and so this is what finally you are going to get here. Now, and you can actually see that if you keep the strain level constant, what you are going to get is, to reduce the damage due to fatigue, we need to minimize the energy dissipation. So, what we are going to minimize? We are going to minimize G star times sin delta. Okay. So, we need to understand what this essentially means. So, if you really want to reduce the damage due to fatigue, we need to basically minimize the energy dissipation. So, what it means, any fatigue damage process also involves substantial amount of dissipation, because you need energy is going to be dissipated when the cracks are propagating, when new surfaces are being generated here. So, we are going to minimize the value of G star times sin delta. So, if you are going to minimize the value of G star times sin delta, how will we write the text here, the spec here? We are going to write G star sin delta, no matter what happens at any given temperature, it should be not exceed a maximum value as far as this parameter is concerned. So, if this parameter keeps increasing, what will really happen? The energy dissipation also will be more. So, that means the tendency for the material to crack will be there always. So, you keep a maximum value here. So, let us understand this very carefully. So, this is for fatigue. So, for rutting, what we did, we wrote something like G star by sin delta, and we mentioned a minimum value. If there is a minimum value, so that means the material is stiff, the tendency for the rutting will be less. As far as G star times sin delta, when you have it as a maximum value, the tendency for the fatigue damage will be lower. I hope this is very clear here. Okay, so this is the basic definition that one needs to, the basic derivations one need to know about how the PG criteria were evaluated. Now, what you may also want to understand is, though we mentioned about stress control as well as strain control, in the linear viscoelastic regime, it does not really matter whether we do a stress controlled experiment or a strain controlled experiment, as long as you are in the linear viscoelastic regime. So, if you go and look at, in fact, you can do this as an exercise. This standard will be shared with you. You can find out what are the strain levels that are specified for unaged, short term aged as well as long term age. What are the Since most of the rheometers these days do not necessarily differentiate between constant stress or constant strain applications, normally what we do is you can specify what is the strain level to be used, and based on this we compute the G star sin delta values and then use it for our PG specification verification. Okay. So, as soon as this lecture is over, I suggest that you should go back, look into the ASTM D7175 and find out what are the strain limits, and it will be part of an assignment problem that you will be submitting it here. So, this is as far as the high temperature PG and intermediate temperature PG is concerned. So, when we were discussing about the various test procedures that we will be discussing for low temperature PG, I mentioned at the time that we will be looking into these 3 standards separately. So, the first one is ASTM D664, So, in the next 20-25 minutes we will be talking about the flexural creep stiffness of asphalt binder using the bending beam rheometer. Then in a separate session we will be talking about D6723 as well as D6816. Okay, so that is necessary for us to understand how the whole PG is written here. So, this is the standard. You can see that this was originally written in 2008 and it was reapproved in 2016, standard test method for determining the flexural creep stiffness of asphalt binder using the bending beam rheometer. It is normally designated as BBR. Okay. So, for us to understand and use this bending beam rheometer, we need to recap some of the elementary beam theory that we have studied in our mechanics of materials course. So, this is very familiar to all of you. So, what I have written here is a midspan deflection of an elastic prismatic beam of constant cross section when it is loaded in 3-point loading. PL cubed by 48 EI is well known to you. P is the load that is applied, L is the span length, E is the modulus, I is the moment of inertia. Now, what we do is we are going to rewrite this and write in terms of the moment of inertia also. If we take a rectangular prismatic beam of constant cross section at its midspan, one can take the above equation, rewrite to get PL cubed divided by 4 into B, B is the breadth, H is the depth times delta. So, this is what we are going to use here, and of course, the maximum bending strain, if we continue on the same way, you are going to get it as 6 delta H divided by L square. These are some of the derivations that all of us who went through an undergraduate civil engineering program would have already finished in our mechanics of material course. So, now comes the most important thing. Why are we now talking about elasticity theory when we very well know that the material that we are going to use is viscoelastic in nature? In fact, what we are going to do here as far as the low temperature is concerned is we take a beam something like this, we apply a load here and we find out how the beam is deflecting. Okay. Now, using this elasticity based formula, we compute two things, one is the midspan deflection, other is the stiffness, and using this length geometric properties, we find out what is the stiffness, and we also want to find out what will be the slope, whether the material will catastrophically crack. In fact, the idea of this low temperature PG is you take any material, you subject it to a very small load, see how it is sagging and when it is cracking. So, that means if we could find out what is the evolution of the stiffness, the deflection as well as the stiffness, we can clearly find out where is the maximum change that is happening, and it is more or less the point in which the beam is going to catastrophically crack. Okay, so that is the whole idea, right. But if we have to use it, we also need to be aware of the fact that even at minus 20 degrees centigrade, we are going to test the material can behave like a viscoelastic material. So, when we write all these things as part of the elasticity theory, how are we going to do it? So, here comes a very, very useful and important principle that is well explained in any textbook in viscoelasticity. What we can do is we use what is really called as the elastic viscoelastic correspondence principle. If you take a graduate level course on viscoelasticity, you will be taught this particular principle in which we will take well known solutions in linearized elasticity and then we do a Laplace transform and try and find out what could be the equivalent solution in viscoelasticity. So, there are many criteria, constraints, conditions under which such transformation is possible, but since that is not part of this particular course, we will not be discussing all these issues here. So, what we are going to do is we need to be aware of the fact that in the linear regime, one can appeal to linearized elastic solution to linear viscoelasticity. So, what we will do is we will take the value E that was shown in the earlier one, what is really called as the flexural modulus, right. So, this particular E, and we are going to substitute it with 1 by d of t, and this is nothing but your creep compliance. If you recollect the material functions that we introduced in the earlier lectures on viscoelasticity, we introduced a creep compliance function, we introduced a stress relaxation function, all these are in time domain. In frequency domain, depending on whether we were controlling the stress or controlling the strain, we introduced g of omega, j of omega. In addition, we also introduced the phase angle function. These were all dependent on frequency here. There is also a popular way of designating d as compliance, it is nothing but j of t. So, this is a terminology that one should be familiar with, right. So, I can also substitute E in terms of what is really called as S of t, and we are going to call it as the flexural creep stiffness, okay, right. So, then what is this flexural creep stiffness? So, this is the formula, it is the same formula that we have used earlier, except that what we did, we made this as a function of time, we also made this as a function of time, and we designated this as S of t. Do not get confused with the phase angle for which we have been using delta. This delta is nothing but the midspan deflection. Such terminologies where the same symbol is used for to mean different things, should become self evident as we are going through. So, we are not really talking about the phase angle, we are only talking about the mid span deflection. Okay, right. So, it is given here as PL cubed divided by 4 into BH cube times delta t, and this is the deflection of a beam at a time t. Okay, and please understand this delta of t as well as S of t indicate that the deflection and stiffness are functions of time. Okay, right. So, let us go to the next thing. So, how is this actually this test is carried out? You can actually see that there is graph 1, this top one, in which a load is applied. This load consists of two parts. There is a contact load, okay, and there is also a test load, and there is something called as a seating load. So, if you look at the seating load, it is the same as the test load. So, as per the procedure, what we do is we load the sample in 3-point bending, we apply a seating load, and then immediately what we do, we release the seating load and bring it such that the remaining load, that will be the contact load, will be there, and wait for 20 seconds, and then we apply the test load. This duration can be is based on whatever is the specification that you want. So, this experiment consists of just applying a constant load and trying to see how the deformation is increasing. Please understand, I will also be reiterating it later, there will not be any recovery in this test. We will be just loading it and see how the deformation keeps increasing. So, please do not get misled by whatever is mentioned in D6648. Okay. So, this is going to be the deflection, this is taken as the 0 time, and this is how the deformation is going to increase. Okay. So, the first and foremost thing is apply a constant test load of this much for 240 seconds, and we will collect the midpoint deflection of the test specimen at some select time interval, and I have made this slightly different. We will know what it is, 120 seconds and 240 seconds. Now, what is the temperature at which we should be doing this test? We will be doing this test at the PG low temperature. In fact, what we want to do is whether the bitumen that we are going to use will be able to withstand the low temperature conditions prevailing in any geographical location, correct. So, we will be testing it at the PG low temperature. So, how does the output looks like? So, we will use the deflection here, collect the midpoint deflection, then use this formula, okay, because we know what is the load that is applied, we know what is the span length, we know what is the width of the beam, we know what is the depth of the beam, and this is the information that we collect from the test. Substitute this and we are going to get this particular graph. Okay, so, we will get the creep stiffness and we plot log of creep stiffness versus log of loading time, and the slope of the response, that is called as the m value, is used as a specification parameter. So, how do we do it? First and foremost thing is, what we will do is, we will first, we have to curve fit this stiffness that you are seeing here in a, we are going to use, basically we are going to use a high second order polynomial and we fit this now. So, because we need to really find out what is the stiffness, this particular slope value that we want to do. So, for that we have to curve fit this whole thing, and there is a procedure that is presented in the ASTM standard. You can take a look at it, more or less it looks like this, right. So, you take this data, fit it to this equation, find out A, B and C, and then using this you evaluate what is really called as the m of t. M of t is nothing but d log s of t divided by d log t. So, you do that and you get the m value. Now, what this particular value, the stiffness value means is, if I take it from the specification, it says the maximum value of the stiffness should not exceed 300 MPa. Of course, these correspond to the temperature in degree C. So, that means if I use any Pg for which the low temperature is, let us say, minus 12, at minus 12 the maximum stiffness should not exceed 300 MPa. In addition, the minimum value m that you see here is 0.3. Now, where should I evaluate this m? See, because I need to substitute some value of t here. I will know how to find out b and c from this expression, but what do I do for t? And that is what I have underlined here. So, I will collect the midpoint deflection, and at 60 seconds I will compute. In fact, you can actually see 60 seconds here. I will compute the m value, and that is the value that should be 0.3. So, this is the spec that one need to use, right. Okay. So, now we can use this standard for unaged, short term aged as well as long term aged, and it is also very clear that we can use this for only for in the, if the flexural creep stiffness is in the range of 20 megapascal to 1 gigapascal, and the test specimen, it should not a deflection more than 4 mm, or it should not be less than 0.08 mm. It should not exceed 4 mm, it should not be less than 0.08 mm, and we do not do any recovery measurement here. Okay. So, this more or less completes our discussion that we wanted to have as far as D6648 is concerned. In the next session, we will talk about D6723, and then using this value 2 standards, we will find out what to do for D6816. Okay. Thank you very much.